The Boston Network Operators Group met on September 29, 2016 to hear a presentation by tech startup 128 Technologies. The discussion is aimed at network engineers on the topic of rethinking from the ground up how routing is done. In this presentation by one of 128 Technologies' founders, Patrick Timmons, you'll hear the problems they were trying to solve and the fundamentals of the solution they brought to market as a result. If you're in the greater Boston area and would like to know more about the Boston Network Operators Group, take a look at bosnog.org.
Thank you for coming. I'm one of the 7 co-founders. I didn't know Andy was going to be here. As it turns out, my beginnings of the story starts with Andy. The 7 co-founders all came from another networking company based about 5 miles north of here. We worked in the telecommunications industry. We built an appliance that was used for securing and interconnecting voice and video over IP networks. And around 2011, this picture was taken at our offices just up near the Bedford line. And then Governor of Massachusetts, Deval Patrick, came. We were a big Massachusetts employer, and so he was coming to press some flesh and kiss some babies and whatnot. And I don't know if it was because Andy has some sort of latent desire to become a politician, or if he was just drunk with power or swept up in the moment. But he had 2 admonitions that day. One was, make routing great again. The second, let's build a firewall. This was 2011. And so, meanwhile, 2 floors above where this picture was taken, our engineering team, who had spent 10 years building this hardware appliance for securing networks, voice and video networks, had been employed by our customer base to start looking at the then emerging NFV field. Like, what can you guys do? And we had invested tens of millions of dollars, if not more, building every one of our hardware platforms that scaled to 50,000, 80,000, 120,000 concurrent phone calls. And they said, build it in software. We said, can't be done. Can't be done. They said, come on, build it in software. All of our other vendors are moving to software. And we said, can't be done. But 2 floors above, while this picture was being taken, our engineers were evaluating it. And much to our surprise, software running on commodity hardware, not purpose-built hardware that cost tens of millions of dollars and years and years and years to engineer, commodity hardware and software were meeting or exceeding performance in just about every metric. And it was at that moment that we knew that we were on the cusp of a revolution in networking. And so, we went through with our plans and we built an NFV, a software version of the platform that we had spent a long time building as hardware. But it started to beg the question, well, what's next? What's next? I mean, yada, yada, yada. The company was sold, and the 7 of us that founded this company got fed up working for the acquirers. And so we put that knowledge to use, and we started to look long and hard at IP routing. We were voice and video guys predominantly, and not all of us, but the lion's share of us were voice and video guys for our career. And so we looked at IP routing through a different lens than traditional data folks may. And we looked at things as sessions. Like a phone call, you pick up the phone and you dial some digits, and you initiate a call, and there's somebody else on the other end of that receives the call. There's a directionality to who initiates that telephone call. But once it's established, there's a symmetry. You're talking to each other. And that sort of signaling, that approach to session orientation via a signaled exchange was something that was really percolating in the background as we were moving forward towards our NFV plans and what's next after our previous company was sold. And so we started to look at IP routing. And this slide here Just a disclaimer, most of these are not my slides, except for the one with Andy, I just start out with a gag. But so if I fumble through some of the builds and all that, please just forgive me. But this slide here represents the promise that RFC 1771 made in 1995 as the internet was starting to take off, and the pundits at the IETF said, we'll make a stateless routing network, we'll have security at the endpoints, everything will be stateless, and so if there's any failure, it gets routed around. It's very simple, very easy. Of course, BGP4 had, I don't know, countless revisions. I've never seen the IETF move so fast as they did when they were revising BGP4 to account for things like classless routing versus classful routing and all that. But anyway, simple. It was built to be simple. But when you look at it, and of course I'm preaching to the converted here, but the reality is it's anything but. And it's not stateless because in order to get the services that your end users want to consume to work, you have to put stuff in the way. And the stuff that you have to put in the way are firewalls and load balancers and overlays and all, DPI, whatever, all of these different middle boxes. In fact, we built a middle box at our last business. I'm well acquainted with middle boxes. And so this is the reality. It's not a simple stateless network. The routing plane may have been stateless, but there's state all over the place. And Andy mentioned, just coincidentally, he and I didn't plan this or anything, but he mentioned that if you could go back in time and tell the 1993 us what 2016 us is observing, that you may have done things differently. Well, I don't know if the time was right in 1993 to have a stateful routed network. Cisco and other router vendors at the time were just doing everything they could to stay afloat and make routers that were keeping up with the speeds and feeds that the booming internet was demanding. And it begat industries like firewalls and load balancers and other middle boxes. But now, just as we learned our lesson at our last business about how you can, against all disbelief, take these functions that were once solely in the realm of purpose-built hardware and do it in software. And so now, not only did we decide when we founded this business to look at software-based routing, but we thought, well, what else? I mean, there are software routers out there right now, but what else? How could we design things differently? How could we avoid this, take our heads out of the ground and say, routing isn't stateless. Look at this. And so we had a vision, the 7 of us, 2 years and 2 months ago, and it was for creating a secure vector-routed network. And I'll explain later in the presentation what I mean by secure vector routing. But really, it's all about getting packets from where they start to where they end in a predictable way, in a scalable way, and in a secure way. Meanwhile, if we can get rid of the middle boxes along the way, all the better. And so I'm going to talk about some of the scale, I'm going to talk about some of the simplification attributes of our platform, and some of the secure attributes of the platform. I don't have slides for all of these things. I'll be happy to just be extemporaneous about it or whatever. So our software was built from day one. And my colleague, Mike Bai, who runs engineering, this was his #1 mission when he built our engineering team, was to make something, one software platform that scales from the smallest needs to the largest needs. And the way we did that, the approach that we adopted, was we looked at what a chassis-based router looks like traditionally, which has a control plane and various line cards that you insert and you add to your chassis when you need more capacity. We reinvented that as software, and then we blew it up. What do I mean by that is, we took the components that make up a chassis-based router, the line cards and the control plane, and we developed each of them in software, and then we allow you as a network designer, network architect, or network engineer to disperse those components in your network wherever you want. It's not drag your packets to this chassis, it's put the components of the chassis where the need is. Make everything a routed network. Have everything be its own network segment. And so we call these different components. The line card, this thing right here that says slice. It's an acronym, software line card engine. A slice is our software line card. The control, obviously, is the control plane, and we use these different icons you'll see sprinkled throughout the presentation to represent the control function, the slice function, or when we have our whole logo intact there, that's what we call a combo, which is a portmanteau of the slice and control in one package. And it was this distributed architecture which allows us to scale from branch size, running on these little NUCs or nukes or however you pronounce it, these little small micro form factor PCs running our combo software, all the way up to a data center where you can add as many line cards as you want to. It's not like a chassis that has capacity for 8 line cards. Have 800 line cards, 8,000 line cards. It's unfettered by any constraints imposed by hardware. And so it's the scalability that is granted to us by virtue of the fact that it's software. Some photos of some of the equipment that we took in the lab over here earlier today. There's a little guy over there, fits in your briefcase. It's a quad-core Atom processor. The street price of that hardware is, I don't know, $150 or something. We take it out to demos and whatnot. That we call our Noisy Cricket. That's the Men in Black reference there. It's the little gun they gave Will Smith. But the Noisy Crickets will do about a gigabit of traffic with today's software. It's pretty beefy for a $150 little hardware platform. And then we've got these 14-core Xeons that we've got running at 40 gigabits, all software. And these, what are those? I can't tell in the picture. Lenovo or Dell or something. I mean, it's a couple $1,000 piece of hardware, getting 40 gigabits of traffic. I learned on the Packet Pushers podcast while we were working here at this business that the Cisco ASR 1000 series router, I think it may have been their first 10 gig platform geared for enterprises. It took them 7 years to build and 3 acquisitions to design the silicon. And we don't have any of those challenges anymore. It's completely different now. The game has totally changed. And not only can we just take the packets up in software and decide where to route them and then fire them out, but we can do interesting things to them en route too. It's not like we're beholden to the decisions made when we put these ASICs onto the motherboard and cast them aside. So let's take a closer look. This is a logical diagram that shows at the top our control function, and here are the slices. Again, I showed in the previous picture, these two things can be co-resident in one logical software instance. It's not like they're managed independently. In fact, like a chassis-based router, even if you cast these software instances of slices and controls strewn about your data center, cast to the 4 winds, you manage it like one logical router. There's no logging into 1,000 CLIs to manage discrete entities. All of these things are viewed through a single pane of glass, single management instance, single set of APIs, netconf, a single CLI, single GUI, all of that. I also want to point out that this may smell a lot like OpenFlow or something. It's not OpenFlow. Packets don't come into these slices and then fly up to the control for it to do some consultation and advise the slice on how to do its routing or packet forwarding. The control is really your policy engine. It's where you decide how you define the services your network is bearing, the properties that those services need to have, and yes, any of the traditional routing behavior, the BGP neighbors and communities and confederations and all of that stuff gets provisioned here, and all of that policy gets pushed down to these slices. And these slices operate independently. I mean, they're operating based on policies. They learn from the control, but they effectively operate independently. They have their own RIB. They have their own forwarding table. They have their own instance of all of the policies that's been pushed down. This is not an open flow-like model. I also want to point out while I'm here that this fast lane here, that's an homage to the 128.2. You'll see references in our software and our marketing and everything to different roadway, like we have a service area and a fast lane. It's just, like to have fun with it too. But in the slice, each one of these packet forwarding engines is where all of the heavy lifting is done. So packets enter into the fast lane. The fast lane is what's doing all of the, your standard fare for packet processing. It's doing all of your policing and your shaping and your DSCP marking and your queuing and your scheduling and your transmission. All of that happens in software in the slice. The slices communicate with each other over what we call the IP fabric. There's no fabric backplane in a chassis anymore because you've dispersed these components. Now your IP network, your layer 2 or layer 3 network between these slices becomes the fabric, as it were. And so we call that network between these guys the fabric. And then packets come in. The slice determines based on the policy and its configuration where the best destination for that session resides. It chooses its complementary slice. It does some voodoo that I'll cover in the next slide, sends it off to its complement. That slice takes that information, it unravels it, and it fires it off to the destination. Any questions so far? Okay. So here's the session-aware data plane, we call it. So a lot of the magic that the 128T, we call it 128T, a lot of the magic that the 128T router does is in the first packet that's received for a new session. And again, think of this through the rose-colored glasses of someone that's coming at this from a voice and video over IP background, where every IP session that exists between a client and a server or two endpoints, or two hosts, looks like a session, a bidirectional exchange of packets. There's a request generally and a response, with very few exceptions. So the source transmits packets to the 128T router. The 128T router says, hey, I've never seen this session before. This is a first packet. Maybe it's a TCP SYN, maybe it's a UDP packet from some source IP and source port and dest IP. The tuple is unique. And it says, hey, this is something new. The slice looks at its policy to figure out where to send it. And again, all of the policy is resident in every slice. There's no open flow. That packet stays local to that slice. It looks at its policies. The policies can be based on current capacities of the links between it and its counterparts, or the capacities of the counterparts themselves if they have some session thresholds that you've set. It can look at the quality of the link between the two devices that it's proactively measuring using BFD and other techniques, and it picks the best destination for that particular traffic. It takes the original source and destination addresses present, the S and the D, and it puts those into what we call the metadata. First packet, we're just talking about the very first packet of a new session, by the way, that's it. It takes the original source and dest address, and it packs them into this header that's maybe anywhere variably between 40 and 50 bytes. And it puts it into that metadata, and then it assigns what we call 128T specific waypoint addresses. Just like a pilot, when he's making a flight path between two cities, has to decide on a series of waypoints, control towers, that it's going to check in at as it goes from its origin to its destination. We adopted that same term, waypoint, to describe the source IP address and the destination IP address of the routers themselves. So this slice here is going to select a source waypoint and a destination waypoint. It's chosen the terminal 128T complementary router based on policy. It picks its own waypoint. It picks the far end guy's waypoint. And it does a double NAT. It then sends the packet on its way. The underlying network forwards the packet to that destination waypoint, which is owned by that other slice. That other slice unpacks the metadata, and it does some authentication checks. It does some integrity checks. The metadata isn't just source IP and destination IP and all of that. There's other secret sauce in there too. It unpacks that metadata. It reconstitutes the original packet, the TCP SYN or UDP datagram or whatever it may be, and it fires it onto its destination exactly the same as it was emitted from the source. So between here, double NAT. As it egresses, it's as though nothing had happened. Yeah?
You're saying it picks the source, right? Is there any situation where the source wouldn't always be the egress kind of router on the way out there? Like, would there be a situation where it picks another source that is not the one it exits out of? It sounds like it's always going to be that same one if it's the session-based style.
I'm not sure I understand your question 100%. So you're saying if this guy picks...
So I get you're saying it picks the destination. I
Yeah,
get that.
okay.
And then you're saying it also picks the source. Wouldn't the source always be that?
It is. I should have clarified. It picks a source IP port tuple.
Oh, okay.
And the source IP port tuple, that waypoint, and the destination IP port tuple, the destination waypoint, are unique, are globally unique. And so that 5-tuple of source IP, dest IP, source port, dest port, and transport protocol, that unique 5-tuple represents effectively a session key, uniquely identifying that session.
I just wasn't sure if there was a situation where it would pick a different source, go a different way on the way back. Kind of.
It wouldn't. No, it would always pick its own self.
Well, I mean, to get a little bit more specific, if that leftmost slice had multiple egress interfaces and the best path was a different internet link, that would be a different source.
Right.
But it would always be the same pair, mated pair.
All right.
Correct.
Are there intermediate 128T routers as waypoints, or is that just IP fabric?
There can be. There can be. You mean once this guy receives it, could he then fire it off to another 128T?
You said you had a source and destination waypoints.
Mm-hmm.
Are there intermediate 128T waypoints? Potentially?
Yeah, potentially. Sure. Like this guy could pick his next hop waypoint, and this guy could in turn pick a next hop waypoint as well.
Gotcha.
In fact,
Each of those hops has an IP fabric in between, probably?
yes. So just by way of example, we've got a field engineer, sales engineer that lives in Seattle. And he has his own home office. And we've got we're eating our dog food in the closet, the IT closet in the corner of this building. He's got one of those little Intel nukes running our software in his closet. And one of our first experiments when we got all of this stuff working a year and some months ago was to do what I've just described. Now, then we hired some guys in Japan, and they said, well, hey, we want to get on board too. One of our Japanese field engineers took one of these nukes and put it in his lab, and he relays packets to headquarters via our Seattle field engineer's home lab. So,
Because you figured out that was better than just the direct internet.
well, it was mostly just to goof around with it, because we like rolling our sleeves up and doing weird stuff. Yeah, he could have come directly to us, of course, but yeah. All of the traffic that we generate out to the internet or anywhere else, for that matter, from this building goes through our product. And so, there's a lot of important things that our people are working on here. And so when someone needs to go make configuration changes on our router, it's not like, hey, let's just go make some configuration changes and see what happens. So it was easier just logistically for us to experiment with the fella in Seattle than it was for us to experiment with the one in a closet. But it could have been just as easily the other way. And basically the same thing happens in reverse. Conceptually, it's the same thing that happens in reverse. So The SYN I showed in the previous slide, assume it's a TCP SYN that goes from source to dest. That server that receives the TCP SYN generates a SYN-ACK, fires it back the other way. The slice that's there will insert reverse metadata, or what we call reverse metadata. It's just backward packet processing that basically does the exact same thing, although there's no need to pick waypoints anymore. Those have already been selected for this session. But the reverse metadata that goes from the second slice in series to the first can include metrics on path performance and utility. For example, this slice may be, you know, a small little form factor guy that's running out of gas. He could put on some active suppression to say, hey, you know, no more traffic for a little while. I got to cool off. But the metadata includes some stats and metrics and other utilization data so that the next time a new packet comes to this original slice, he can make a more informed decision about where to send the next traffic that arrives. And so that's really the gist of how our packet processing engine works between the two slices. It's a double NAT. All of the decisions are made by the first slice. They're abided by the second slice in line. Although this is not just taken at face value. As I mentioned, there's encryption and authentication and all sorts of other security functions that this slice can and will include as it's forwarding packets over to its counterpart, so he can do some integrity checking to make sure that it's not just some, you know, rogue agent firing packets at him. And all of this, this mucking around that we do with the packets is completely transparent to the source and the destination because it's all unwound before it leaves our fabric.
So if you have a slice in here and a slice in Seattle and a slice in Japan, is that all one router or is that three different routers?
It can be all one router. The way that we've set it up today is as 3 separate routers. But again, it's just as much for our guys to just, you know, have something to play around with in their own labs. They each have their own lab setups that they're playing around with. But yeah, they could all be 3 slices within the same router, absolutely. I neglected to mention that the choice of these waypoints ensures, or enforces, I should say, some modicum of path symmetry. Just like the example I gave with the pilot who puts out the flight plan, says I'm going to go from Logan to SFO via this set of waypoints I'm going to check in with. Now, the flight plan for this pilot may differ slightly from the flight plan of another pilot. You know, they may take different approaches and all of that. They're still going to check in at the same waypoints. We couldn't guarantee that the first packet from the source to the dest is going to follow the exact same network path that the second packet from the source to the dest is going to take, because there may be other, you know, ECMP or other happenings going on in this, either this side of the slice or that side of the slice. But these waypoints here, and because the IP addresses are owned by the routing elements, ensure that we're going to see all of the packets symmetrically for both sides of the session, the forward flow and the backward flow. It was this enforcement of symmetry that really got us thinking that, you know, if we do this and we're assured of seeing all of the packets in both directions of this IP session, then we can start to do some interesting things. And that was one of the sort of, what's the word I'm looking for? It was one of the concepts that we had for eliminating all of the, or as many as we can, of the stateful devices that exist on today's networks, the middle boxes. Oh, okay, the middle box. So, as you guys know, middle boxes are everywhere. I read some white paper that was published in 2012 by some Berkeley students that said that the number of middle boxes on any given enterprise is approaching, if not exceeding, the number of routers that are on those middle boxes, on those networks. And every one of these middle boxes requires subject matter expertise. It requires management and maintenance and all sorts of this periphery that makes these networks more complicated. And you got VLANs, you've got Q and Q, you've got tunneling, you've got all sorts of stuff just to get packets to flow the way they want to go. And our argument is that, well, our waypoints can be used to direct these packets where they're going. And if we can see both sides symmetrically of an IP session, then why can't we load balance them? Why can't we act as a firewall? Why can't we do all of these NATs and carrier grade NATs? And if we're seeing all of the packets for all of these sessions, we can come up with some really cool analytics to show our end users on the behaviors of their network while we're at it. And so we feel that by subsuming some of the functions that these middle boxes are contributing to networking today and putting them arguably where they should be in the router, Andy's flashback in time and build a router in 1993 that can load balance and be a firewall too. Today's technology makes it a reality. I mean, the behaviors of software and the performance of off-the-shelf compute means that we can follow Gordon Moore's law and say every 18 months our routers are going to be twice as fast. It's not going to take us 7 years and 3 acquisitions to make something better. We could just ride the curves. And so that's the idea.
But with that functionality that's there, normally I pay for that. I buy a middle box. Are you saying I just get that, or is this something I license up to?
You get it. Yeah, we don't have any individual licensing for load balancing and firewalling and all of that. It's part of the base package. Yeah, so as I mentioned, when a slice gets a packet in and it goes through its policy decision, like what do I do with this? You can tell it the capacities of all of the links on your network if you want. You can tell it the capacities of all of the other slices that exist in the network. You can apply administrative costs too and coerce packets into specific ways if you're so inclined. But you're not beholden to that. These things can be configured to do whatever you want to do. And if you want to load balance, you want to send some this way and some that way, that's fine. What our approach to firewalling, I think I get to it in a couple of slides. If I don't, then I'll talk about it off the cuff. But I earlier mentioned that I would get to our topic of secure vector routing. I'll dig in a little bit now. Our route policies that you define on the 128T router are slightly different than you would get in a standard BGP routing table. It's not like the wild and woolly days of 1995 internet where you have these massive routing tables of classful blocks that are exchanged and everybody knows about every other classful block. The way that we do it at 128T is you define policies from source endpoint groups to destination services. It's a service-oriented approach to describing routing. And the way we've broken it down, our data model discussion, a data model we use to drive our router, it's a much longer conversation. So I'll just set the table a little bit. We describe our configuration either as top-down, like you define the services that your network is going to carry, your web services, your database services, your voice services, your video services, conferencing, whatever it may be. You define the properties of those services, the addresses and where the servers live, the thresholds for acceptability for traffic, like no more than 1% packet loss or no more than 100 milliseconds latency, whatever they may be. You define your services in our data model, top down. Likewise, bottom up, you define the actual components that your network is built from or your 128T network is built from. You define the slices. You define the interfaces on those slices. You define where the control functions live. And then the combination of the service definitions and the network definitions are collapsed and wrapped with a big policy layer that you can define when those services get accessed and by whom. The primary way that we partition our traffic sources is in what we call a tenant. A tenant is a group of endpoints that all share some common properties. And you define your services to exist logically within these tenants. So by way of example, in our office here, as I mentioned, we use our own product. We have a few tenants defined. We have an engineering tenant where all of our developers' machines exist. And the engineering tenants, the tenant for engineering has some services that have been defined for it. Our source code repository, our QA test machines, our documentation store. All of these things are services that our engineering team has access to. So they're defined within that tenant. We also have another tenant that's defined here with a set of machines for our HR and finance team. And they have payroll information, and they have hiring plans and budgets and all of this stuff. And the services for them are defined in that tenant. Now, if I'm part of the engineering tenant, I don't even know those services exist. It's not like I send a request to the finance server and I get rejected, or I don't know what the username and password, and so I get unauthorized. No route exists. I can't get there. There is no route. And so my packets from my laptop as a member of the engineering tenant have no way to get through our network to those servers. There's no security better than inaccessibility. And so by defining these tenants and the services within them and wrapping them up in the policies, then you can address this, this notion of network security in a very different way. Any questions? Okay. I think I'm wrapping up here. I was told I had limited amount of time. I don't want to bore you guys. I'm not going anywhere, so if you have questions, you can certainly ask me over a beer. So we have, we weren't targeting ourselves at any particular market. I mean, the routing market is really what we're after. But it's not like we're looking just at branch office or enterprise or data center. We're looking at everything. Anywhere a router exists, and maybe some places where routers don't yet exist, is where we're looking to put our product.